刚刚下去问说，那个系办有没有人跟我一样头晕？他们说没有啊。你们有人跟我一样这2天会头晕吗？那我这样不妙了，我可能真的要去看一下医生。好 ，OK， 那我们继续哦 ，OK。那 So we know like yeah, we want to do this problem reduction, right? To construct this NP-complete set of problems. But you know, if you have one NP-hard problem, you can use the technique just described to prove other problems are NP-hard and NP-complete. So we need an NP-complete problem to start this off. So we need a first NP-complete problem, okay, to do this job. So we want to find a problem that are at least as hard as anything. Okay, so how, you know, are there really such a problem? Okay, it is. Okay, there is. Okay, there's a theorem called Cook-Levin theorem. Okay, called the satisfiability problem. They say the satisfiability problem, or abbreviated as SAT, is NP-complete. Okay, so they proved this, okay, directly, okay, in 1971. 1971 is about like a little bit more than half a century ago, okay. At that time, computer science is still at its infancy, okay. Most of these are mathematicians, okay. They prove the same theorem has been proved independently by another guy, okay, in Russia, okay, Leonid Levin. Okay, so that's why it is called Cook-Levin theorem, okay, because the same theorem have been proved by 2 different set of people. Okay, this Stephen Cook, if I remember correctly, he's American, and this is well, exact to make it more clear. 这是苏联啦 ，USSR，OK， 苏联现在已经不存在哦。对，严格讲起来，你现在听到俄罗斯跟苏联应该是不一样的东西哦。USSR 其实当年苏联包含很多地方，包括那个什么很多东欧的国家都是苏联当时的一部分哦。那个包括现在的那个他们不是那个战争吗？那个俄罗斯跟那个乌克兰战争嘛，乌克兰当年也是 USSR 的一部分，所以我不是很确定这个 Leonid 这个 Levin 是哪一个现在哪一个国家不知道 ，OK。So in this theory, they show that any problem that meets the definition of NP, okay, as long as they satisfy the NP property, can be transformed in polynomial time to a CNF formula. Okay, it's a conjugate normal form. Okay, conjunctive normal form. Okay, what is conjunctive normal form? We are going to talk about that. Later. Okay, but the proof of this is outside the scope of this course. Okay, so you don't need to worry about that. You just need to remember, SAT is the first NP-complete problem. Okay. What is SAT? Okay, you don't know CNF, but at least you have learned discrete math, right? So you know like you can use like you can create a very complicated logic clause, right? Logic so like something like this, right? Okay, so given a Boolean expression on n variables, is there a possible assignment, okay, to make this expression true? Okay, so this shouldn't be too difficult to understand. The problem itself shouldn't be too difficult to understand, as long as you learn discrete math, right? 在那个离散数学，你有学到逻辑嘛？对不对？你知道说你可以用这个 and or 什么 implication 啊、not 啊这些东西来，还有一些这个刮胡，你可以做一堆这个东西，然后把它弄得很复杂，对不对？Okay, and then if you have n variable, Boolean variables, you want to be able to, to tell, okay, from this formula, is there a possible assignment that can make, this expression to be true? Okay. Oh, by the way, let me make it clear. Okay. In the following discussion, we usually only discuss decision problem. Decision problem. You might imagine that a lot of decision problems could be expressed as a complex logic expression. So what is decision problem? Decision problem is the problem with that you have to answer yes and no. Okay. For example, the SAT problem is a decision problem, right? Okay. And a lot of decision problem can be, yes, Cook and Levin, they prove, this intuition is correct. Okay, they actually prove the general result that any NP problem can be expressed into a logical expression. Okay, so that's very, very profounding. Okay, profounding. Okay, so. But the SAT is too difficult. Okay, we are going to, the general form, any given expression, logical expression, it could be very complicated. So we want to simplify it a little bit. Okay, so the first thing we can simplify is we can convert any logical expression into conjecting normal form. Okay, so we can simplify the Boolean expression. Okay, so what is conjecting normal form? Conjecting normal form means, okay, let me define a few terms here. Okay, a literal means occurrence of a Boolean or its negation. 就是要不然就是一个变数啦，要不然就是 not 一个变数。那叫 literal，OK，然后我们有这个 a Boolean formula is in conjunctive normal form, or called CNF. Okay, if it is an and of clauses, each of which is an or of literal, such as this. 就每一个刮弧是一个 clause。在刮弧里面都是 or 一些这个 literal 的 or， 那刮弧跟刮弧之间是 and， 这叫做 conjective normal form。那you could simplify any given Boolean expression into conjective normal form. Okay. For not, that's easy, right? So if not is outside of parentheses, you can assign that you can assign the not into a parenthesis by using De Morgan's law, right? De Morgan 定律可以让你那个 not 如果在括弧外面，可以把它放进去，对不对 ？And like if you have some like a parenthesis, there's like a distributive law, right? 就是分配率这些东西，你就可以把它展开来，就变成那个比较简单形式。唯一一个可能要讨论就是那个 implication 嘛 ，A imply B. This is not A or B, right? A imply B is not A or B, right? 对不对？要不然是 A 是 false 嘛，要不然 B 是 true， 对不对？对不对？所以 all this can be converted into like a lot of and or. With some arrangement, it is relatively easy to convert any Boolean expression into CNF. And then we have a special SAT problem, okay, called 3SAT. 3SAT. What is 3SAT? 3SAT refers to 3CNF. So each clause has exactly 3 distinct literals, such as this. OK， 上面这个不是嘛？因为上面这个最左边这是2个，最后面这是1个，只有中间这是3个。那这下面这个 3CNF 是不是每一个都是3个？对。So arbitrary SAT expression can be translated into CNF forms by introducing intermediate variable. 这个把那个 expression 哦，就是 Boolean expression 变到 CNF， 这个我就不细讲了，因为这个其实需要一些induction 的这个证明啊。对，如果严格去证，那我刚刚就是用叙述一下，让大概知道一下而已。对，但是有一个事情是很好玩的。Called 3CNF problem or 3SAT problem. Okay. So satisfiability of Boolean formula in 3CNF form is also NP complete. 所以我们把刚的 SAT 就任何的 Boolean expression 转成 CNF， 这个是 equivalent 的嘛，对不对？我们没有损失任何东西。但是如果把 CNF 转成 3CNF， 它还是 NP hard， 还是 NP complete。Okay, it is still NP complete. Okay. Here it says like the proof is done by Cook, like part 2 of Cook's theorem. But it's not that hard to show SAT. Okay, I mean 3CNF can be reduced to SAT. Okay. The reason we care about the 3CNF problem is that, or 3SAT problem, it is relatively easy to reduce to other. 你可以用这个来 3SAT， 用这个东西可以证明很多的问题是 NP complete。OK， 所以我们对这个会比较有兴趣哦。OK， 那所以我们要怎么先证明说这件事情哦？这件事情，那我只要讲，我可能没有时间，因为今天只剩下1个半小时，我们要把后面那些全部讲完了，我有点怕讲不完。我这边不直接讲那个严格的证明，我只讲I will only talk about how you can convert any CNF, because we know any Boolean expression can be converted into CNF, right? So now I only need to tell you, okay, any CNF can be converted into 3 CNF. That's good enough, right? Okay. And this reduction, this conversion is also in polynomial time. Okay. So because it's already like this, right? Already like this. So it's not 3 CNF just because of 2 possible reasons. First, it doesn't have enough literals. Like 就是它可能一个 clause 可能只有一个或两个，对不对 ？literals。OK， 这是不够的。另外一个 it has too many， 对不对？就只有这2个情形。好，那我们处理这2个情形就好了。我就好。譬如说，如果有一个 literal， 像这个，还是头有点晕。好。Okay, this one, you convert into this. Okay, remember, new variables are your friends. New variables are your friends. Okay, 假使 P 跟 Q 是 new variable, assume P and Q are new variable. Okay. 我从那边从2个开始讲好了，因为从1个开始讲，我怕你们会混淆。I'm afraid you guys will be confused if I start with like a 1 literal case. It's x1 or not x2. Let's convert this thing into a new variable, P. Not P. This is identical to this one. Right? Because regardless of the value of P, you have to have one of them to be true, right? I mean, this has to be true in order for this end to be true, right? Okay? So adding this P allows you to have 3 literal in 1 clause, right? So you are going to expand this 1 to 2 clauses. 1 clause into 2 clauses, but with new variable, I mean, each one will have 3 clauses, literals, right? So, the last one. The conversion idea is exactly similar, okay? You just need to introduce 2 new variables. Well, we have Q, so use Q, we have used P, so use Q and R. Not Q. Q not R. Not Q not R. So we expand one literal into one clause into 4 clauses, each one with 3 literals. I mean, the idea, the concept is the same, right? I just introduced all the possible combination of this Q and R. So in order for all this AND to be true, your NOT X5 has to be satisfied, right? Has to be satisfied. So that's exactly just like this, right? Okay, so I have done with the case that is too short, right? How about the case that is too long? Say we have a clause P1 or P2 or or PK. Okay? Then what I can do is that I can make P1 or P2 a Q. Okay, I introduced a new variable. By the way, this Q is assume Q is a new variable. Okay? And then it's going to be let me see. Yeah. R is also a variable. Let me see. P3. Let me see. I made a mistake. I remember there's there's a one case. Let me just use where is it? This one. This one. Okay. If a clause is a long clause, L1, L2, blah, 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 to LK, okay, then it becomes this one, L1 or L2, blah, 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 or LK minus 2, or U, where U is a new variable, and LK minus 1, or LK, or not U. Yeah, I made a slight mistake. So Q, this is not Q. Yeah, but anyway, you get the idea. So first, by introducing this new variable. The length here gets reduced by 1, right? 这个长度就变短一个，对不对？那你多了一个 clause。OK， 多了一个 clause， 然后3个 literal， 那这个减一个，那你可以继续做这件事情，对不对？一直减到说前面这个变成3个，对，这第一件事情，你可以一直减下去。第二件事，我要跟大家讲 ，Let me tell you, the top one and this one are equivalent. Why? Because okay, either this is true or this is true, right? So either this is true or this is true, or this, when this is true, this must be false, right? So this one must be true, right? Okay, so it's either this is true or this is true, right? So that's exactly this one, right? 了解这意思吗？所以 okay, if the clause is too short, we have a way to deal with it. If clause is too long, we have a way to deal with it. Okay, so it tells you, okay, and this reduction obviously is polynomial time, right? Okay, because it takes, if you have k literal, it takes big O K to reduce this whole thing into like a 3CNF, right? Okay, so the whole thing, must be done. The conversion from CNF to 3CNF is polynomial, right? It's polynomial. Okay, and it's so that's you are converting because it's conversion, so it's exactly the same thing. So if you are able to solve 3CNF, you are able to solve CNF, SAT, right? Okay, so that's pretty much tells you that 3CNF or 3SAT is an NP complete problem. Okay? They are basically the same problem. It's just like you are writing the problem in a different format. Okay? So, we sort of already proved like 3CNF or 3SAT is also NP complete. So now, okay, we are in a position to talk about some problems that are NP complete. Okay, so we know SAT is NP complete. Okay, we know 3CNF SAT or 3SAT is NP complete. So in this class, I'm going to tell you clique and the vertex cover are NP complete. We probably don't have time to talk about subset sum, Hamilton cycle, TSP. There are too many. The book talks about more examples. The textbook talks about more examples. And if you are interested, by the way, this reduction is not necessary only this path. There are many different. Remember, I told you all the NP complete problems are reducible to each other, right? So it's just some reduction are easy to construct, some reduction are difficult. Okay, so here it's one of the easy reduction paths. Okay, and if you are interested in the NP complete problems, and the discussion, okay, there's a classic textbook. It's a Gary and Johnson, okay, Computers and Intractability. It was published in 1979. At that time, there are already thousands of NP complete problems. Okay, remember the first NP complete problem was proposed, was brought up in 1971. So 1979, it was like less than 10 years, right? They are already, hundreds, thousands of NP-complete problems out there. Okay, but I used to have this book, but I lost it like when I moved back to Taiwan. Okay, it's a very interesting book. Okay, because like in my master program, I used to, originally I wanted to study like logic and 后来交了女朋友，知道要结婚的话，就知道说不能饿死自己了。饿死自己就没关系，不能饿死老婆跟小孩。后来就没有往这边走。Okay, so now we are going to talk about reductions to prove some problems are NP complete. Okay, so we are going to talk about K-clique, K-independent set, K-vertex cover. Okay. So I hope we have enough time. Okay, we should. Okay, but this reduction, it takes some, what should I say, effort to understand. So we already talked about 3 SAT, right? Or 3 CNF SAT, whatever you want to call it. Okay, so given 3 CNF formula, okay, is there an assignment of true false to each variable to make the formula true? Okay, so this is like a 3 SAT. One example is like this. Okay, in this particular example, there is a possible assignment to satisfy this expression. This is clause, these are variables. And this assignment will make the whole expression true. You can have a look. For example, x or y or z, right? X is true, right? So because x is true, so this one is true, this one is true, right? And then because u is true, so this one is true. And u is true, so this one is true. So z is false, so not z is true. So the whole thing is true. Okay? So this is one possible assignment. I never say this is the only assignment, right? There may be more than one, but remember this is a decision problem. So we just ask you yes or no, right? Is there a possible assignment there to satisfy, to make this expression, Boolean expression, or 3 SAT, 3 CNF Boolean expression true? Okay, so this is one of possible assignment. Why do I provide this answer? Because we are going to use this as a running example. So next question is K-clique. Do you know what K-clique is? No? Okay. We want to show K-clique is NP half, NP complete. Okay. So when if you want to show a problem is NP complete, okay, there are 2 steps, right? First, to show the problem is NP, and then use a reduction, right? Okay, so first let me tell you what K-clique problem is. Okay, clique is a complete subgraph. Okay, so for example, in this graph, this part, this green part is 3 clique. This red part is 4 clique, right? So K-clique problem is asking, given a graph G and a number K, is there a clique of size K? Okay, this problem is NP complete. How do we prove that? first, we need to prove that this problem is NP first. To show this problem is NP, it's very easy. We just need to give a polynomial time to verify the answer is correct. And then we need to show it is NP hard. So we are going to give a reduction from a non-NP hard problem. So we are going to do that. Okay, 3 SAT, okay, K-click. Okay? So first, okay, you want to show an answer is is a solution. You just need to randomly, okay, given a K nodes from this set of vertices. You try to pick K vertices and verify if every pair has an edge, right? So it doesn't take much time, right? It takes at most polynomial time, right? No problem, right? If K is 4, well, it just, because we are not talking about like you try to verify all the solution. No. You just try to verify one given solution. So for example, you just get the vertex 1, 2, 3, 4, and then you verify any pair of these 4 nodes that has an edge. Okay, it's going to be C4 too, right? At most, you just need to take this much time. So that's pretty much like a K squared, big O K squared. It takes that much time to verify it. So this is this is very easy. So once you are done, okay, the next part is to show that, okay, you are able to reduce. This is easy, okay. You just assume this is the solution, one possible solution, then BDEF. So BDEF, the verification just check if any pair of these 4 nodes has an edge, okay, have an edge. So check for certificate. So it's like the time is like bounded by V square. Square of number of vertices. So that's pretty much like a polynomial. Okay, so that's it. So the issue is the total time is going to be polynomial V plus E. So we are done with the first one. The second one we need to show its NP half. Done with the first one. Remember this process. Okay, so now let's assume we are given this 3 SAT instance. Okay, how can we construct a graph such that if there is a K-click, then there's a possible assignment to make the whole expression true. Okay, so we need to construct a graph. Okay, and then if there's a click, we have a way to find the assignment to make this expression true. Remember, this reduction, this mapping, both ways have to be in polynomial time. Okay, so how to do that? Let's do it this way. For each clause, we introduce a node for each of its 3 variables. So you see, x, y, z is here, right? X, Y, Z. x, y, y bar, y. We have x, y bar, y here, right? And the u, y, z bar. U, y, z bar is here. And the z, x bar, u, z, x bar, u is here. And the x bar, y bar, z bar is here, right? Okay, so we have one node for each of the literals. Okay. And then it's tricky part. For each, we add an edge from each node to all non-contradictory nodes in the other clauses. As long as they are not contradicting to each other. What are the nodes that contradict to each other? X and X bar. You cannot have a link between them because they contradict to each other, right? Okay, so it's something like this. I mean, we don't try to draw the line for all the other cases because it's going to be too complicated. I'm just going to use X from the first clause to draw like a non-contradictory edge to the clauses. I mean the second clause and third clause. I mean you need to complete the whole thing, but I will stop here. Just want you to understand. For example, X and X, they do not contradict to each other, right? X and Y bar, that's fine. X and Y, that's fine. X and U, again, there's no contradiction. X, Y, it's okay. X and Z bar, that's fine, right? But you don't draw to, for example, X bar. Okay, you don't draw to this one either. Okay, so but you do draw the line from X to Z, the Z here, from X to U, from X to Y bar, from X to Z bar. It's just like we omit these lines. Okay, we omit these lines. So you do the same for Y, do the same for Z. So it's going to be kind of complicated. Okay? So just remember we do this. Okay? And then let K be the number of clauses. K be a number of clauses. So we are claiming there is a K-clique in this graph if and only if there is a satisfying assignment in the original 3CNF. Why? Well, it's a break time. Let's take 10 minutes break. When we come back, we will continue the discussion here. I want you guys to think.